Hi, welcome everyone. Yeah, this is yet another ML talk, I suppose. That's how it goes these days. Yeah, so we would like to talk about our project that we got into over the past few months. But maybe first of all, we should introduce ourselves, I guess. Yeah. So my name is Kacper. I'm a Goldsmiths electronic music computing and technology graduate. Currently studying in The Hague. I'm doing master's research in digital synthesis. Yeah, and that's it about me.
Yeah,
here's Ben.
I'm also a Goldsmiths postgraduate, and I'm pottering around teaching as a sort of associate lecturer and doing silly projects like this.
Yeah. So how did we get into this topic in the first place? Well, I guess it kind of started with the presentation at the end of our course, where we saw Dave Griffiths, and he showcased his project where he was trying to approximate samples, one-shot samples, using a TX7 and genetic algorithms. Yeah, and we thought, oh, okay, this is like quite a cool idea. We were, I guess, into reverbs at the time, and we figured, okay, what if you can do something like that with feedback delay networks? Maybe what kind of ML you can use to do so, to approximate the parameters that will give you something as close as possible to a real room impulse response. Yeah, so it's a pretty known problem, I suppose, in the domain. It's been around for a long time. So I guess one of the kind of early takes on it is Judd's paper on analysis synthesis, right? So you analyze a room impulse response, and based on that, you try to get the parameters for the feedback delay network to synthesize. Well, you put an impulse through it, right? And then you end up having a room impulse response that is somehow synthesized to be as similar as possible to the target. Yep. So yeah, here's a little disclaimer. So with reverbs, generally, if you're modeling a impulse response, you can kind of split it into two things. So you have the early room reflections, right? And that is usually being dealt with using finite impulse response filters. You would often, I don't know, truncate a part of the original rare recording and convolve that with the signal you're putting through the network, and later on you would blend that with an FDN that gives you the late reflections. So in this talk, we'll be only focusing on the late reflections, leaving out all the fair solutions and convolution-based architectures. Yeah, so take it away, Ben.
Thanks, Kacper. Yeah, so I think we sort of delineated this project into two roles. DSP is my sort of field of interest, but I'm by no means an expert, but I was kind of responsible for creating a feedback delay network that Kacper could then sort of integrate into the machine learning environment. So we use Python. So I'd just like to give a little bit of a background of my sort of experience learning how to write a feedback delay network and writing a reverb in Python in general. So just a bit of background, there are other types of reverbs. I'm sure you probably all heard of Schroeder, well, you might have Schroeder reverberators. We started using this system to begin with because there are fewer parameters to train and the architecture is a lot less complicated, so it was easier to implement. Yeah, so Schroeder reverberator, so Schroeder described it in his 62 paper as a natural sounding artificial reverberation, and describes a sort of colorless artificial reverb achieved using all-pass filters. He also states that you need 1,000 or more reflections, and a flat amplitude response using all-pass filters. Arguably, 1,000 or more reflections isn't maybe not quite enough to achieve a realistic sounding reverb, but for 1962, I think it's a reasonable approximation. And this particular arrangement, which was the one that we implemented to begin with, is SatRev, implemented by John Chowning in 71. So we've got 4 feedback cone filters and then 3 all-pass filters arranged in parallel and series, respectively. And this is kind of indicative of the sort of like common approach. But I'd just like to point out that Geraint Luff and Sean Costello of Valhalla, not both of Valhalla, different, Geraint is Signalsmith, points out that there are other sort of topologies that Schroeder outlines in his paper, and although this one's like used a lot because it's like featured on CCRMI website, it's not the only one. And Schroeder actually describes a system where there's 5 all-pass filters with a feedback path that leads back to the beginning, and then that creates those sort of late reflections. And in his paper, actually, I think what he's talking about is that system, which will have taken a lot of time to compute, but will have ended up with quite a more natural sounding decay because it would have had a lot of late reflections. Yeah, so this is what I'm talking about, possible improvements. He also talks about nested all-pass filters. And then, yeah, so what he's trying to achieve is this great echo density or large echo density. And yeah, so what does this mean? Why is this important? There's a really good diagram by Savelimiki in the paper 50 Years of Reverberation that has, yeah, this image of, in the late reflections, you can see that there's a single impulse that's been passed through a system, and then towards the end of the system, we've got this sort of like really sort of stochastic, noisy signal, and you can sort of test reverberation systems. Oh, I just moved away from the mic, sorry. You can test reverberation systems like this by passing in a single impulse, and when you're using an FDN, you can create you can try and approximate constant white noise by passing in a unit impulse and then generating as like stochastic or Gaussian distributed system as possible. So yeah, so we moved on to using an FDN so that we could get those late reflections. So what is a feedback delay network? So you can describe it as a state-based space system. So it's a multi-input, multi-output system. So we've got several parallel delay lines and what's called an orthogonal mixing matrix. So an orthogonal mixing matrix is, I'll actually talk about this later. It's a matrix that when you take the product of itself and the transpose, you end up with the identity matrix. So a matrix where all the values are 0 except for a diagonal, where there's 1 for every value in the diagonal. It also can be described as a vectorized comb filter. So this is a single input, single output system, and it can be made all pass by feeding a feed forward path not featured here, back into the system before the output. But with a multi-input, multi-output system, this is a little bit more difficult to configure, and that's why you need a Hadamard matrix or an orthogonal matrix to ensure that it's a uni all-pass signal. Yeah, okay, so that's what I've just talked about. Sorry. So in terms of the development, I've got to give credit to Geraint Luff of Signalsmith Audio. I think his tutorials are really, really good. And it was really useful having those tutorials in order to understand how this multi-input, multi-output system works. So what I ended up doing was creating small bits of code that implemented each part of the multi-input, multi-output system, right? So Geraint describes it as a multi-channel signal, which I think just made it easier to sort of understand. So here's my multi-channel signal with a single impulse on the first, let's just, it's a unit impulse, split into 4 channels. Right? And then, So split it into a multi-channel input and then pass it into their respective delay lines. And then here I'm just going to explain how I chose the delay line lengths, right? So I use this prime power list and it's indexed with an exponential curve. And then I also have to ensure that no primes repeat. So I generate a big list of prime numbers, and then I use an exponential curve to index this large list of prime numbers. But the larger the exponent, which I'll get to why that's important later, this is sort of the early reflections thing, the larger the exponent, the more likely it is that you will index the same power number at the beginning of the curve. So you have to make sure that you check that each subsequent or the next number indexed in the list is not the same as the previous one, because it's the flatter the beginning of that curve with a larger exponent, the more likely that is. And then this exponential list is co-prime, which is really useful because it means that you can squash and shrink the delay times but then each delay line will be mutually prime. And we need them to be mutually prime, or we want them to be mutually prime in order to generate, in order for it to be less likely that you will end up with repeating reflections. So if you have a unit impulse in your signal, actually no, I'll just go back to that slide. Yeah, if you have a unit impulse and they're not prime, or they're repeating at the same delay time, then they'll cancel each other out because they're not just values from 0 to 1, but they're also bipolar. So you end up losing some of your signal. You end up with phase cancellation, or you end up with superposition where some signal sounds louder, and it doesn't sound as it's not as like evenly distributed. So this was the first stage. So the matrix has to be is orthogonal, and that's in order to ensure that the feedback delay network is all pass. And then you also scale it. So you create a matrix. We used a Hadamard matrix, and then we scaled it so that the values produced by the product of the vector input signal and the matrix were equal to 1. And that's really useful because it means you can do things like generating infinite reverb time. So if the gain value is 1, then it won't explode, but it will just repeat indefinitely. We take the product and then we spread it over all the channels. And then also an important note, but this isn't what I did, is that Hadamard can be constructed using recursion. So in C++, you can construct a Hadamard recursively because of the type of matrix. So you can see that this whole Hadamard matrix, this 4x4 matrix, can also be split into 4 individual matrices. The top left, top left, top right, and the bottom left are all the same, but then the bottom right is the inverse of the other matrices. So you can construct larger and larger matrices by recursively calling itself. So it can be quite fast if you're doing it in C++. However, I was doing it in Python, and I just called scipy.hadamard. I did try writing it myself, and I was trying to port the Geraint Luft's C++ code into Python, and that was difficult. So a word about the mixing. Like I described earlier, in implementation, you treat this multi-channel signal as the matrix, and you take a product of this matrix on the right with this matrix on the left, although they're swapped in the code. So you can see here that some of the poles are some of the signs are inversed. So we've got this column of all positives, floats, 0.25 each, and you can see that the first channel or vector are all positive signs, and then that the second channel corresponds to the second column, and the third and the fourth, and so on. You can see you've got negatives in the middle, and then positive, right? So it's useful because it also inverts the signs, and then it makes a nicer sound. I can't tell you the math behind how that works, I'm afraid, I'm sorry. So you mix the signal, and then you keep doing this process, right? Mixing the signals together, and then delaying them, and then mixing with the matrix. And then I'd just like to briefly talk about some of the failures in my implementation, right? So before I did this process where I sort of plotted each part of the FDN out, I sort of kind of had this bullheaded approach where I was like, yeah, I'm just going to write an FDN, and then just did it thinking that I knew how it worked. And what I ended up doing was calculating the impulse response for each delay through a whole pass of the system. That doesn't really make sense. What I mean is that when I implemented it and I was looking at C++ code, I was kind of doing it sample by sample. And the way that I did it is I took the first delay and kind of processed a whole feedback through a single impulse, and then moved on to the next delay. And I was mixing down to each channel as I was doing that using the Hadamard. But what that results in is effectively a kind of series of all-pass delay lines, where then if you took the end, you'd end up with the same topology as if you just connected all these delay lines one after the other. When what you want is a mixing and a parallel, which you create through the Hadamard matrix, right? So then you get few reflections, and I was, of course, taking the output and summing them from all those delays, but it's not the same thing. I only realized this when I did some sort of, just auditory testings between like already developed FDNs that I knew had a similar architecture, and realizing that mine did not sound anywhere near as good. And then there's also some like summing failures. I'll sort of outline how this looks in the code. It's really important when you're working with multi-input, multi-output systems that you sum in the right place, right? Because if you don't, you then end up with these phase cancellations. And what I was doing is summing here, right? And you can see the issue. I've got no, you'll end up with no values in anywhere but the first index where you'll have a big value, right? So it doesn't sound very good. So what you need to do is make sure that you sum here, right? So you do the delay, then you sum, pass it back through. And then I'd like to point out as well that there's ways that you can improve this. I think the Velvet noise algorithm also adds a little bit of delay time to each of the, a little bit of random noise to each of the delay lines. Because, yeah, I mean, some of these are pretty, like, close to each other, and that's good, but it can definitely be improved. There was some optimization that we did. We used JIT, so just-in-time conversion, which I think kind of, like, bounces down Python code into just-in-time compilation in C++. And in order to do that, I needed to adjust the exit condition. So previously I was using a while loop, and then checking that the last product of the matrix was equal to the previous iteration in the loop. And if they were equal, then that means that I'd gone through every possible permutation. But for JIT compilation and for, yeah, there was a really good talk yesterday about how this actually works. For JIT compilation, you need to, JIT needs to know ahead of time how many loops there are going to be in order to properly vectorize the code at compile time. So yeah, for loops need exit conditions in order to do that. So so in order to calculate that, I just used the T60 time for the smallest delay line, and that meant that I'd looped through every possible permutation in order to, yeah. So it was a little bit funky, but yeah. So this is the code, and then there's a few extra bits that I haven't spoken about here, right? So yeah, so I've mentioned where I'd done it wrong, and then I hadn't mentioned how I'd done it right. So not doing it in C++, but doing it in Python meant that I could sort of do a feed-forward pass over the length of the whole unit impulse, and then mix, and then go over again, and then make sure that that ensured that I could mix everything through one loop through the system. Yeah, and then another thing is that in the JOTS reverb, he implements like a really very elegant solution to calculating relief T60 times, so the sort of damping filters for small reflections. My implementation is nowhere near as elegant as Josh's. I just used a one-pole filter in the delay path, and then made sure that the curve for the one-pole filter and the curve for the delay line kind of correspond. And then, yeah, take the output. And yeah, so that's the code. So that left us with a few parameters. We had the minimax values for delay times, the sort of frequency curve to get darker or brighter rooms, and then the decay time. The implementation in hindsight is a little bit funky, so I did something weird where I calculated the T60 time for the whole system, independent of the minimax values for delay time. So no matter the size of the room, it meant that we could generate impulse responses of any arbitrary length. That was to generate like an artificial data set where we could use the T60 time as a label into our system, which it maybe in hindsight makes for a not very good reverb, and we probably should have done that a different way where we just calculated T60 times from real reverbs. But it's an interesting note. Yeah. Okay. So that's how the FDN was made, and I'll pass you back to Kacper.
Yeah. Yeah. All right. Cool. Yeah. So what we ended up with, well, I guess maybe we should first have a look at like generally like surveying through papers of people approximating FDN parameters. There's a bunch of stuff you can try to optimize, right? So you have the T60 time. You have the cutoffs of coefficients of decay filters. You also, in case of like the JOTS FDN, you have the tunnel correction filter at the end. So these two, like Ben said, they are related to the T60 time. So essentially, if you calculate that, you don't really have to care about these. You would only care about the output gain and the delay line lengths. And in the paper by Primavera, where they actually use some like funky stochastic gradient methods to approximate the parameters, they also tune the feedback matrix. So this is not what we're doing. We have the Hadamard matrix. It mixes things fair enough, so we stuck to it. What we ended up choosing to tune, and that was kind of following the workflow of Jay Coggin, who was also using the kind of JOT-like FDN architecture. We decided to go with the T60 time. Again, the delay line lengths, and as Ben explained, we have them. We are not trying to approximate them separately as free variables, but we're kind of generating this list, right? To simplify things. I mean, this was essentially, at first we used it to just simplify the data generation process, because if you generate the list of delay line lengths in that way, they tend to sound decent, right? Because we wouldn't really need, like a completely random distribution out of which, a huge chunk would actually sound super crap. So we broke it into 3 parameters, right? We have the minimum and maximum of the delay lengths, and then we have the mapping curve. And it's a similar case with the decay filters, right? So we have the one-pole filter cutoff frequencies. And again, you just give it a min and max, and you give it the mapping curve. And all of that stuff to make it kind of trainable as smoothly as possible. We just normalize everything to 0, 1 inside of the function. And inside of our FDN function, it gets remapped. Well, it gets mapped to like a range that's suitable for the cutoff or the delay length. So the further deal would be to pick what features we actually want to use when, what features to use when we're calculating the loss function or the cost function if we decided to use some other stuff than neural nets. With common stuff. I forgot to include. Well, I guess you could just not do any feature extraction at all. You could just compare signal to noise. You could do the signal to noise loss between row waveforms, but that's kind of pricey. So I mean, of course, we have the spectrograms. You can do the bar coefficients. You can do the MFCCs. You can do like log mil spectrograms, whatever you like. But across throughout the papers that we went through, these 3 seem to be like most prominent. I mean, of course, you usually just would use a spectrogram. Okay, so in terms of machine learning approaches in general, you can actually start really simple, right? You don't have to go with neural networks. That is kind of I guess a big question for a lot of problems. Like, do you actually need to do all this highly computationally expensive stuff? You could actually use more classic ML methods, right? So for example, you could use a hill climber method, right? Where you just try to find a local minimum of the cost function. You randomly generate parameters at first, and with every step you just randomly deviate to some direction in that space, and you just see if your cost function gives you a higher or smaller value. If it's smaller, well, you take that as your next step, and rinse and repeat. Another pretty common approach is genetic algorithms. So this, in a sense, well, that sounds kind of suitable, right? Because you don't have to deal with all the problems with like backprop. You just, you can again, you have your parameter vector, right? Set to some random state initially. You generate a population of kind of that with slight mutations. You take out the best ones that minimize the cost function. You take them and you kind of generate the next population with that, again, with some mutations, right? So for example, Coggins did that. Another paper that we looked at was Matthew E. King's and Fedden's and DeVerno's paper where he was actually comparing several methods, right? So he was using neural nets. He was using, like the OG multi-layer perceptron. He was doing LSTMs and bidirectional LSTMs. You can see it's 2018, right? Yeah, and the funny thing is it turned out the hill climber is actually very consistent, and it performs better than the MLP. And yeah, the only thing that actually was better than that was like a bidirectional LSTM architecture, and it was not as consistent in terms of results. Yeah, and then you have more recent approaches like the Lee, Choi, and Lee implementation, where they have an autoencoder, which is like a general purpose autoencoder trained on tons of impulse responses. They map the impulse response to a 2D latent vector, right? And based on that vector, you train projection layers that project these two values onto parameters of your reverb. So kind of this big model is agnostic towards your network, but later on you can kind of tune these little projection layers to fit with your FDN architecture. Yep. Okay. Yeah. So here comes the question of the mapping. Yeah. So what can you actually do? Well, if we say we pick, okay, let's do it with a neural net. You have, yeah, again, quite a few options. Well, we definitely want the network to output parameters, right? Because that's what we feed into our FDN. So this is kind of, this is what we want. So this is not really up to dispute. But in terms of inputs, right? We could do the raw waveform, or we could do the spectral features. So that's kind of a question. Well, yeah, I guess again, this is a bit more expensive. So also because of the architecture we based our project on, we went with spectrograms. And then also there's a big question of targets. Like how do you compare what you're predicting to what you're aiming for, right? So you could do it kind of in the simplest possible way and calculate the loss between the parameters, right? But then you're kind of making the assumption that, okay, if we have a small change in the reverb parameters, that will result in a small change in the perceptual quality of the impulse response, right? Which is, well, it might not always be true, and also, it will be a really it kind of gets really fiddly with the mapping part inside of a function as well, right? Because if you have like I don't know 0.001 difference in the parameter which is responsible for the frequency curve mapping, that might yield very different results than the same value deviation if you relate it to the decay time. Yeah, so it's kind of a tricky problem. And then, yeah, with end-to-end training, which we'll talk about later, you can also compare the spectral features, right? So generally, yeah, we will input the spectrograms, but we could, if we manage to put our FDN inside of the training loop, then for each generated set of parameters, we could, plug them into our FDN, put an impulse through it, and later on, take the spectrogram of the impulse response of that FDN and compare it to the original output, right? And that kind of would make sense, right? Because then we're comparing the perceptual qualities instead of these abstract parameters that, well, I mean, well, they are related to how it sounds, of course, but yeah, we don't know, like, okay, how direct is this? Okay, yeah, so. Yeah, so we can, okay, let's say we pick the features, we picked what we want to input, we picked what output we want, what targets we chose. Yeah, so the kind of, I mean, this is quite basic stuff, right? Like what kind of cost or loss functions we considered. So since we're not actually doing any classic ML problems, we're not doing like, yeah, we're not doing genetic algorithms where we would, for example, have to get a bit more involved. With the cost function, we're just using, like a classic loss, mean squared error. An alternative is if we're dealing with spectrograms, we can do the multi-scale spectral loss, where you take the target spectrogram, you subtract every sample of the generated spectrogram or the predicted spectrogram, right? You take the absolute of that value and you sum them all together. And you do the same with the log of the spectrogram, and then you have the sum of the errors in the in the normal spectrograms, right? And you have the sum of the errors in the log spectrograms, and you just kind of multiply the second by whatever your alpha coefficient is. Yeah. So let's get on with it. Okay, so let's get into the implementation. So the first thing to do is, well, if you want to train stuff, you probably need a GPU. So big shout out to Goldsmiths College for letting us rinse their resources. Yeah, and this actually initially it turned out to be quite tricky. I mean, I don't know how many engineers who work with this stuff we have in the room. I assume quite a few, and maybe that's like a basic thing. But I mean, when you're actually getting into neural nets, yeah, this is kind of tough, right? Like you need to learn like all the workload managers, all the scheduling stuff, how to get your GPU drivers to work, all that kind of thing. Yeah, so actually the environment setup, I think initially it took me quite a long time. I think it was a good few days, of like exchanging emails with the sysadmin. Yeah, big shout out. Yeah, so yeah, let's say we have the environment ready, right? We have all the Python libraries installed. Everything we need is there. Could the drivers work, right? So what then? Well, we need to generate our data, right? So our FDN takes parameters in the range normalized to 0, 1. Okay, and how we did it is we could of course just take a bunch of random distributions and throw at it, but Ben was not very satisfied with the initial results, so he like tuned them a little bit. But it was a matter of just kind of restricting the ranges or like offsetting a little bit. Maybe like offsetting a bit the decay value, or kind of quite obvious stuff like you want the min to be, if you have like a minimum and a maximum for a list you're generating, you want the minimum to be smaller than the maximum, right? So you need to restrict the range somehow. Yeah. So what we did is, I generated like 3K samples by feeding a bipolar impulse response through a 16-channel FDN that Ben implemented. Yeah, so I don't know if you explained that, but well, initially we tried with like a unipolar impulse, but then you end up having like a lot of signal either above 1 or below 1. So yeah, having a bipolar impulse where you just have like a 1 and a -1 that tends to work better. It's kind of more even. Yeah, and in terms of the number of channels, we kind of estimated that, okay, 4 and 8 didn't sound so good. 16 is kind of the minimum that we would like to go with because it just sounds all right. Yeah, so this actually takes a while. Like, I mean, even with the JIT compiled number functions, we were generating at 16 kilohertz. So running it on the Storm server on 64 cores, that took us like an hour to generate 3,000 samples, which is probably not ideal. But yeah, it's also the fact that we are using our own kind of pipeline design from scratch in this case to generate, rather than using libraries that are probably made for that and optimized. Yeah, so we tried. Well, we also experimented a bit with just parallelizing it to speed up stuff, and it gave us an speed increase of maybe like 30% or so. But yeah, then we had some trouble with the parameter space, and occasionally it turned out we were feeding the wrong parameters to the FDN, and stuff would crash. And yeah, it was just awful to debug with running stuff in parallel. So we eventually gave up. Yeah, so we're generating 3K samples. We're calculating STTs of all of that stuff, and we're taking the spectrograms, and we're calculating the log power of these with FFT size of 1024 and hop size of 256. Yep. So, right. So in terms of architecture, what I did is kind of we started with a pretty hacky approach. So we took the neural reverberator by Christian Simons from a few years ago, because it has like a quite friendly pipeline to use for generating all the preparing all the data and training. So we took it as a basis for experimentation, and it uses TensorFlow. so we stuck with that. Okay, so the first thing we tried is kind of the simplest approach that I spoke about, where you try to make a mapping between the spectrogram and the parameters, right? Which assumes you have some direct relationship between the two that makes sense, right? So we just did like regression. So the neural reverberator, it's a variational autoencoder, so it has the encoder and decoder part, where you have like a bunch of convolutional layers that encode the impulse response into, in this case, it's a 3-dimensional latent vector. And then it tries to basically decompress that value and reconstruct it as well as possible. But it was made for generative purposes, and well, we don't really need generation. So we removed the decoder part and just replaced it with a stack of dense layers. At the end, you just basically get a vector of seven parameters. Input is left as in the original, so you have the log power spectrogram, and it outputs a 7-dimensional parameter vector. The target, as I said, it's again the parameter vector, but it's the one that we use to generate the impulse response, of which spectrogram is this, right? And the loss is the mean squared error between the predicted and target parameter vectors. The problem with that was, it was really hard to tell if the spectral features are actually sufficiently related to the parameters. If they're obvious enough to make this mapping, because of course, I mean, you have the feedback part and the feedback delay network, and that tends to complicate things quite a bit, and it turned out to be like not so trivial. So again, this probably, you have better approaches to doing this, like the architecture I mentioned from last year, the paper by Lee, where they have an autoencoder, right? And they keep you do output the parameter vector out of the net, but that's at the very end. And in the middle here, you have the autoencoder that gives you the latent vector, and you map that latent vector to these parameters, right? So again, you have this big model agnostic architecture, and then on top you have like some smaller projection layers that project that latent vector onto these. So that could be a thing to try, I guess. But then the question is also, right, whether this architecture we were using as a base, would it work because it was made for generative purposes, rather than being, like a very general purpose encoder model. So that was the kind of first take on it, right? And then the second thing to try was to design an end-to-end architecture, right, where we would include the FDN in the training loop. So again, the input would be the log power spectrogram. You again output, the parameter vector, of course. But the target in this case would be the log power spectrogram of the impulse response that you've input, right? So these two are actually the same. It's just that when you're calculating the loss function, right, you need to implement your own one, your custom function that generates an impulse response using the predicted parameters, right? So the FDN, you actually have it in the custom loss. You feed it the impulse. You get the signal vector. You do the spectrogram of that, and then you can do either MSE or you can do like the spectral loss, for example, between the log power spectrogram of that generated rear, right, and the target one. With that, it actually gets quite. It gets quite gnarly in terms of the implementation, because first of all, we have our FDN. It's implemented using JIT-NumPy. The base version was done using NumPy, but then the TensorFlow autograd doesn't support that really. So you would need to calculate your gradients by hand for the FDN, and that's like way above my head, to be honest. An alternative would be to actually implement the FDN using TensorFlow, and I attempted doing that a while ago. Actually, I didn't use it. I didn't use TensorFlow. I used Torch, but then you end up with something that's you can use the autogradient, but it's horribly slow. Yeah, so that's a big issue. So yeah, so it's slow, plus it's kind of painful to implement. Actually, I mean, in case of TensorFlow, you have to like replace all the NumPy operations with tensor operations, and it's just, if you're kind of more used to writing DSP code and not doing DSP in a machine learning framework, it's not so nice. Yeah, so probably again, yeah, a solution to this would be, implementing a differentiable approximation of that FDN that you can just run in parallel, like, I don't know, using finite impulse response filters. Like, I think in the paper by Lee, I think they did it using state variable filters implemented with FIRs. Yeah, but again, this is kind of non-trivial and way above our expertise level. Yeah, so this is kind of where we ended up. Yeah, so to recap, what would be the summary? Because there's definitely a lot of things we could approach in a better way. So yeah, I think for me, the kind of big question in the end of all of this was like, okay, do I actually need a neural network to do all of this, right? Was like all the GPU setup, was it worth it? Could I do it maybe, on like my 2012 MacBook that I have in the closet if I used, I don't know, if I used some like basic ML, and maybe the results would be good enough? Well, it might be worth trying. Yeah, then there's the case of, for example, some of the parameters you can derive directly from the impulse response. You don't have to kind of blindly throw them into the neural net and hope that it will spit out the right thing, because the T60 time you can actually calculate from the rear. And then you end up not having to calculate, yeah, like I said, the cutoff frequencies for the filters, for example, right? So you're kind of left with fewer things to predict, which is good. Yeah, a quite basic thing is actually, well, it would be very reasonable to have a baseline, because in this case, it actually, yeah, it's kind of tricky to figure out, okay, what would be a sensible baseline? What I'm gonna do test by hand, I'm gonna like try to approximate it by hand and save like 1,000 examples. Oh, that might be a bit hard. Yeah, yeah, and then the other thing would be, yeah, to implement our FDN in a way that's differentiable and parallelizable, because yeah, if we're using number, we can well, theoretically we could use our FDN in the forward pass, but the backprop, it's just not going to work. Another problem was that running end-to-end training, for example, at the start you would often get values that are quite out of the range of your training data. So you would end up having like negative values and kind of weird stuff that's all over the place. So the question is, how does your FDN function actually handle if, say, like if all of your inputs are negative and it just cuts them flat to 0? Yeah, how do you deal with that properly? And how do you deal with potential blowups of your feedback network? Yeah, and then the last thing would probably be some more efficient data generation, right? Because you do have, even in Python, you have tools for generating artificial impulse responses. And that could definitely improve not only the quality of our training data, but make it maybe a bit closer to real room impulse responses. Yeah, and maybe it would be faster as well. Yeah, and I think that's it, folks. Yeah, thanks.